So welcome back, and today we're going to continue to talk a little bit more about data. But I first wanted to point you to the website again. I don't know if you guys go to the website regularly, but whenever there are updates, so now the slides are there both for this talk and for last week's, and also there is a video both of the lecture and the tutorial session if any one of you missed the first lecture. And the other thing is that the reading list, we've added a document which is Stuart Brown has worked on, Python Basics, which might be could be worth reading. It gives you an introduction in so you can read about it there. The other thing is, which I pointed out last time also, is this data visualization blog that Nature Method has. There's a link to it there also that is very useful. And there are a bunch of short articles, so you can occasionally read one. And it gives a lot of good suggestions on how to do visualization. Then finally, another thing that's new is that we've added a comments box under the lecture. So what we thought that in general you take a course and then you have an evaluation at the end. But then usually one doesn't get very useful and detailed information. And since this is the first time we're giving this class, we really want your comments on what's good and what's bad. So you can definitely comment on the class on Tuesday and the tutorial, but also you should be able to comment on this lecture while it's going on. So if you see a slide that you don't understand, tell me, and then we'll use this to try to improve it for next year. Today I'm going to talk about descriptive statistics. So what we did last time, we looked at some data and we visualized it in different ways. But now we're going to do some calculations to calculate some summary statistics. And probably you're familiar with most of these things that we're going to calculate, like we're going to calculate the mean, we're going to calculate standard deviation and so on. But what I'm going to try to go through with you is how to give you a little bit of feeling of what are the properties of these. And so that's what this lecture is about. And so if you look under the reading list, there are several articles also from Nature Method. So now this is another blog on statistics that I also recommend. That they again write short articles about a specific topic and they I think the ones I've read have been written very clearly, much better than most statistics textbooks that I've seen. And then there is also an additional, if you're really interested in statistics, to read about is Think Stats, which is a free book online that you can read. So this is sort of the general schematic of a statistical analysis. So you have a population that you want to find out something about. And you select, from this population, you select a random sample, because usually the population is too large to investigate completely. So you select a random sample, and then you calculate some statistics on this sample. And this is why this lecture is called Descriptive Statistics, because that's what we're going to do. So we're going to calculate different things and to describe our sample. Then later on in this course, other lectures, you're going to learn about how to make then inferences from the sample statistics onto the population. But that we're not going to deal with today at all. So our population are going to be different distributions. And you're already familiar with the normal distribution a little bit. And last lecture we looked at taking samples from that. So here now we have the distribution on top, and then we've selected different sample sizes. So the first, the figure here on top, we've selected 3 samples, and we've done that 5 times. And then down here, we've selected 10 samples, again 5 times. And down at the bottom, we've selected 100 samples 5 times. So you can see how when we randomly select, this is sort of how the distribution of normal we see. So we see when we select few samples, of course, we have a lot of variation. And we can see if we have 3 samples, like these 2 first ones, they look like it could be quite different because they don't really overlap. But it's just because it's just because of statistical fluctuations. So now if we look at the slightly different distribution. So the normal distribution is nice because it goes down to 0 or close to 0 very fast. It's symmetrical, and a lot of statistical methods are developed for samples drawn from a normal distribution. But sometimes we have skewed distributions. So this is an example of that, of a skewed distribution. So again, we see that on one side, the distribution goes down to 0 fast, while on the other side, it goes down much slower. And then, so if we select samples from this distribution, again, 3 samples 5 times, 10 samples 5 times, and 100 samples 5 times. Then from this, already here, when we have 10 samples, you can probably see that it is skewed. But definitely from the 100 samples, we can see that there are outliers in the direction of the skew. So another distribution we're going to look at is one that have long tails. So this one, it's again symmetrical like the normal, but it has much longer tails. And that we can see here when we select 3 samples, it's sort of all over the place. And also when we select many samples, we see that there are a lot of outliers. And then the 4th distribution we're going to look at is a complex distribution with a lot of peaks. And we can select samples from here, but again, then, and we're going to also calculate the different statistics on this complex distribution just as a comparison. But I mean, the main reason why I included this distribution is that if you have a distribution like that, you shouldn't calculate the mean. We can always calculate the mean of if we have a finite sample, we can always calculate the mean and a variance. But what you're going to see is that it's really not very meaningful to do that. And so that's an important thing to remember. So so we have these distributions, and we want to select, we want to randomly sample them. So how do we do that in a computer? So the one way to do it, so this works for any distribution that you have experimentally measured, for example, or a known distribution. So what you can do is to generate a pair of random numbers. So here we generate a pair of random numbers, and we generate it so that it's within the range. So we generate the x value within the range of our distribution and the y value within the range of y values that we have. So let's say that at random we generated this xy pair. So now this is within the distribution. So then we can keep it. But then we repeat this, so if it's outside, we're going to throw it away. And if it's next one is inside, we keep it, and we go on and do this for as long as we want. And this is a very simple method in a computer to generate any distribution of any shape. And this is can be very useful. There are, for known distributions like the normal and also other distributions that we work with, there are more sophisticated methods that you'll learn about in a few lectures. But for a general experimentally obtained distribution that we can't describe the shape, this is a method that can be used. And actually, to generate all these random samples, this is the method I've used in this lecture. Okay, so the mean. Everyone probably knows how to calculate the mean. And you just take a sample, and then you sum all the measurements, and you divide by the number of measurements. And then you get the mean. So now what we can look at is what's the properties of the mean. So now we have the normal distribution, just to remind you what the distribution is. Then we randomly select a sample size. So here is on the x-axis on these two figures is the sample size, and it goes from 1 to 100. And then we calculate the mean, and the two plots here are exactly the same. The bottom one is just zoomed in. So what we see here is for the normal distribution, if we select very few points, very small sample size, we get a big spread. And then the mean will, and so what we've done, so for each sample size, I've repeated this 5 times. But what we can see is that if we then increase the sample size, the spread of the mean will decrease. And we'll come back to this a little bit later, what the functional form of this is. So then if we look at the skew distribution, it looks rather similar. Again, this is it's not centered around 0 exactly, so it's a little bit shifted, but otherwise the spread of the mean is very similar to the normal distribution. But if we go to the one with the long tails, as expected, we get a much bigger spread than we would get for a normal distribution. And then for our complex distribution, of course, we again calculate the mean, even though it's not a good idea to do that. We get a very big spread. So especially if we zoom in compared to here. So it will be, of course, a much wider distribution. So then some other values that we can calculate is, for example, the median. So here, or we can quartiles and percentiles. So these are different positions in the distribution. And pretty much it's looking at ordering the samples in order of magnitude, and then finding the position. So for example, the median would be the position where 50% of the samples have a value higher than the median and 50% have a value lower than the median. And then we have the quartile, so that's equal to what's also called Q2, so the second quartile. So the first quartile is when 25% of the sample is lower, and then we have the Q3, which is the 75th percentile. So something that we then can look at is also, we can define this for any percentage. So we can, for example, something that could be interesting is to find the 95th percentile, where we find that 95% of the our values are within this range. So these are some other things that we. So if we compare now the mean to the median, so the median is the same as in the previous figure. Now we've overlaid the median, and the median points are in gray. So as you see that the median and the mean has quite similar distribution. The median is slightly wider, just because when you calculate the mean for the normal distribution, we use all the points. So we get better statistics, but otherwise they behave in a very similar way. So if we do this for the skew distribution though, then the mean and the median separates out. So one question, can you see the color differences? Is it, no, you can't. Okay, that's too bad, because I've used these colors throughout. Can you see it if you download the slides and look on your own computer? No? Okay. Sorry, what? Okay. So I will try to find. Yeah, I will try a better one. Okay, so then for the distribution with the long tails, what we can see, if you can see the colors, is that the mean has a wider spread than the median. And that's because we have these contributions from very large, higher probability of large values coming up at random. So we get contributions that are sort of at random very large, while the median is very well defined. So then in the complex distribution, we have actually the opposite, that the median is wider spread than the mean. And that's probably because in the complex we have these peaks that at random, the probability of the median ending up in one of those peaks is quite high. So that, and then we have this wide background. So we will, that's why we will have a larger spread there of the median. So then we have, we can look at the quartiles also. And now the Q3 is in purple and the Q1 is in gray. Now they're a little bit more separated, so they should be easier to see. So again, what we have here is, of course, that Q3 is always, I mean, it's higher than the mean, but the distributions are quite similar to the width is slightly wider than the mean, the distribution of the means, but it's more like the distributions of the median. And again, if we look at the skewed one, we can see the skew, and also we can see that with the long tails we have more of a scatter and more variation. And in the complex, again, we have a lot of variation. Okay, so the one thing that we have these different distributions, but there's one very good thing. We have the central limit theorem saying that if we have different distributions, but we have a non-normal distribution, and we add up samples from them. So like we take a sum, so for example an average, those will be, if we have a large enough number of samples, it will converge to a normal distribution. And this is very useful because we often can take samples from a distribution and calculate the average and do that over and over again. And then we know that these averages will be normally distributed. There are a few caveats though. The values have to be independent from each other. And then you'll hear a lot about independence throughout the following statistics lectures during next few weeks. And the values also have to be from one distribution or from a set of very similar distributions. And the distributions have to have a finite mean and variance, which actually not all distributions have. And you'll come across a few distributions that don't have. And actually the long tail distribution that I've been using it just in the range from -1 to 1. But if you use it from the range from -infinity to infinity, then the mean is not defined for it, and also not the variance. But since it's symmetrical, the median is defined. So then I'm sure you've all calculated the variance. So again, we have a sample. We calculate the mean by summing up the values and dividing by the number of samples. And then we take the difference between, we take the square of the differences from the mean for each point and sum that up and divide by n. And that's the variance, or the square of the standard deviation. So now, again, looking at the variance of the different distributions. So again, just to remind you, on the x-axis here in these two graphs, we have sample size. So from, in this case, from starting at 3, going up to 100. And showing then what's the variance for difference. So we see if we have very small number of samples, then we get a very big spread in the variance, but then it settles down to a level. And again, if you look at the skewed one, the variance is quite a bit wider. For the one with the long tails, and remember, this is only, since we take only look at this distribution between -1 and 1. If we would do it, it would be from -infinity to it would be even worse. But here we see that there is a much larger spread, and the same for the complex distribution, which has again a very big variance. And again, this is just to show that this really is not the right. I mean, this distribution we shouldn't calculate a mean and a variance on. And actually, later on, we'll talk about. There will be a lecture on signal processing, where you learn how to find peaks in complex data. Okay, so then mentioned before the interquartile range. So this is the between Q1 first and the third quartile. So we have 50% of the sample in there. So if we take, we can then, and this is very comparable to the standard deviation for a normal distribution. And we've divided it by this factor just to make it scale like the standard deviation. So again, same colors here. It's gray is the interquartile range, normalized to the standard deviation, which is in some kind of purple. But what here they're pretty much overlaying. Then in the skew distribution, there is not also not much of a difference. But when we come to the long-tailed one, we see that the interquartile range is a much better measure for this distribution than is the standard deviation. And this is the same thing that happened when we looked at the mean, compared the mean and the median. So for this distribution with long tails, the median was a much better measure. And then for the complex distribution, again we have that the interquartile range is a much worse measure than is the standard deviation. So we mentioned the central limit theorem, and this is sort of an exemplifying that. So if we repeatedly take samples of different sizes, so now we're calculating showing the mean on the x-axis here, either when we take samples of 3 and calculate the mean, and then we do that many times, so we get we can make a histogram and get a distribution. Then we repeat this where we take sample size of 10 many times to again get a distribution. And what we see is that from when we go to higher sample sizes, the average is more and more defined, and it's also, as we'll see, for even the other for normal distribution is not so surprising, but what the central limit theorem says is that for our other distributions we will also get that the means are normally distributed. So if we look at the skewed one, if we have n very low, we see that there is a skew still even in the mean, but already at 10 it's a very little tail, and it's pretty symmetrical. And at n equal to 100, it's really has become symmetrical. And the same with our long tail distribution. It has a long tail for small n, but pretty quickly it goes and becomes very close to normal. Now, we're only doing this by looking at the distributions, but later on in the course you'll learn how to test whether a distribution is normal or not. And again, we have our complex, and here the more skewed and strange the distribution is, the more the larger sample size we need to get close to a normal distribution. So here, in this case, we need for the average to be close to normal distributed, we need definitely more than 100 samples, a sample size of 100. So, oh yes. So because of this, the other effect, not only, but both that the central limit theorem tells us that the mean is normally distributed, and also the effect that you see for all of these, that it's a wide distribution when we have a small n, and a narrow distribution for large n's. And this can actually be shown that the standard error of the mean scales as the square root of the sample size. So that's because of this effect that you saw on the previous slide. So then now we're ready to start talking about error bars and other ways. So now we can use these, the mean, the variance, the median or interquartile range, to display our data better. So there is this is one of the articles on error bars on this Nature Methods blog, and so quoting from there, so they looked at all the Nature Methods papers in 2012 and saw that about 2/3 of the places where one would hope there would be error bars had it. And they were, but the problem was that they were evenly spread between either showing the standard deviation or the standard error of the mean, which is a very big difference. And in 5% of the cases, it wasn't specified, which is not good. So the third possibility that people use sometimes is the 95% confidence interval, which is actually in medicine very common, but not in nature methods. So this is also from this paper, and I recommend looking at this carefully. So if we first look on the left here, so it shows the for standard deviation, standard error mean 95% confidence interval. It shows what the p-value is for when the error bars touch. So in this case, it's quite different. So if we compare these three cases, it's the p-values when they touch are really very different. So we really need to know what is shown as the error. Then, for example, if we then look at a common choice of p-value would be 5%. So if we then, for the overlap is very different. For standard deviation, if we show that, there can be a large overlap, but still we have significant results. But standard error mean, there is a gap to obtain that p-value. While the 95% confidence interval, again, there's quite a bit of an overlap. So what their conclusion is, and I think I can agree with that very easily, is that none of these are intuitive. It's not very useful. One does need to put error bars, because at least then that will give you some information about the error. And also one should describe very carefully how one chose the error bars. But to really go from looking at error bars to conclude whether there is a significant difference is very tricky. And so what they suggest is, as an alternative, is that one could select confidence intervals for when the error bars touch at the desired p-value. So it would be 83% confidence intervals for a p-value of 0.05. This is probably a lot of reviewers would complain at this, and it wouldn't be so easy to get through. So probably, so choose either of these, but think about how you're doing it and describe it carefully.
So I have a question. I just got done reading this out of a stats book, and maybe they have described it further, but my understanding was that the standard deviation was to describe the population variance, and the standard error of the mean was to describe your sample that you've taken from the population variance. So in my head, that made it appropriate to always just use the standard error of the mean, because we're not really describing the population.
Yeah, so what we want to see is the reason we make the plots is to illustrate and to try to show whether if there is a significant difference or not. And so it's, I think it's fine to use any of these, and probably their recommendation is probably the best. If the error bars touch, that's at the significance level that you want. That would be probably the ideal. So there is one way to plot things that you probably have come across, which is the box plot. It uses a lot of these different statistics that we've calculated. So what it usually has a box, that's what it's named after, and that shows where the first quartile is and the third quartile ends, and then it shows the median. And then it puts these whiskers at usually 1.5 times the interquartile range. And then it would also show outliers that are outside these whiskers, show each of them separately. And then one can also add this notch for the 95% confidence interval. And so it can contain a lot of information, and it's quite a good way to show data. It's definitely for few points, but probably shouldn't use it for less than 5 points. But for less than, let's say, 30 points or so, histograms, as we've seen, are not so useful. But these can give a very good idea of what's going on. So,
sorry. So the
yeah.
size of the notch. So from so the entire the box in the notch plot is Q1 to Q3, and then there's a little indentation from Q3 up to the median. So I'm
so the indentation is the median and showing the 95% confidence interval for the median. So that's the notch. And so I haven't in this lecture included the confidence interval because that will come a little bit later. Okay. But that's so you there will be quite a lot of detail on how to calculate confidence intervals in different scenarios in the future lectures.
Okay. And is this assuming multiple? So if you have one population and you're sampling multiple times from that population, you should use this notch as opposed to one sample from one population.
No, I mean you can use the notch even for one sample if you can. I mean if the sample is so the recommendation that one usually gives is that the notch, as long as the 95% confidence interval is less than doesn't extend beyond Q1 and Q3. Mm-hmm. Otherwise, it becomes looks very funny. But and also, you should of course have enough samples to be able to calculate the confidence interval.
Sorry, I didn't understand the purpose of the
Yes. So it's showing what the sort of one would expect to have. I mean, it's have most of the data points within the whiskers, and we'll look at some examples to see for these different distributions of how often we get outliers. And for example, if you have a normal distribution. You really, in a box plot, you don't get many outliers in general. And then, well, I'll have some examples of that. So here are a few box plots for the normal distribution. So again, we've taken sample sizes 5, 10, 100. And we've done that 5 times for each. And as you see, there is an occasional, so for 5 here, in this case, we didn't get any outliers. Here is 1, 2, so an occasional outlier. And here, even for the larger sample size, we have just one. But that, of course, varies depending on from sample to sample. So it's very much, it's designed so that for the normal distribution, you would not have a lot of outliers in general. But then, of course, we see that when we go to the skew distribution here, especially for the larger numbers, we have many more outliers. So the nice thing with the box plot is that you can quite easily recognize different deviations from the normal distribution, like that it's skewed here. We can see that at least for the large sample sizes. And the same for the long tails again. Now we see both, in both directions, a lot of outliers. And then for our complex distribution, again, we can see from the box plot that it really doesn't behave very well, and that's because it has a lot of structure. So one other thing one can do, of course, is to overlay, do the box plot, but then overlay all the data points. So this is exactly the same, should be the same. Here we just show the outlier, but here we show all the data points. And that can, that's probably a good exercise later on. You can try, because so Pam is in the exercise is going to go through how to generate all these kinds of plots. And then you'll be able to look at the scripts that were generated, that were used to generate these plots, and you can just to get a feeling for what happens if you have different sample sizes and different kinds of distributions. So it's a very good exercise to see how it varies. So for example, if you do an experiment and you expect that the measurements are from a distribution, it could be worth doing a small simulation to see what would happen for different sample sizes. So now we can compare different ways to show the same data. So this is just now for the normal distribution. And here we have these bar graphs, either with showing the error as the standard deviation or as the standard error. And in general, bar graphs are not so useful to show first of all, if you want to show an asymmetrical error, that won't show up very well. And also, there is a lot of sort of distracting color with the length of these bars. So probably a better way to show it is just showing the average and then the error bars, either as a standard deviation or a standard error or a confidence interval. Or then as a box plot. So what I would recommend is that if you want to show more detail, it's probably better to go with a box plot, either just showing the outliers or showing all the data points. And in this case, for example, what we see from the box plot here, when we show all the data points, is that these three measurements, we had a lot of data, while in these other measurements, much fewer data points, which are lost in the bar graphs and also in when we just show the average and the error bars. So now we can go to the next distribution, the skew distribution. And again, when we use the box plots, we can see that it is a skewed distribution, while these other ways are not ideal. But sometimes you might want to have a very clean graph and just show the essential part, and then I recommend probably to use this the scatter plots with error bars, but don't use bar graphs. So then again, finally the fat tail, how that would look in the same data shown in 3 different ways. And yeah, so I would recommend looking at these and thinking a little bit about how to, what's the best for your presenting your data, and and play around with it and try to look at your data in different ways. That would be my recommendation. See what is the clearest and what shows what's going on best. So now, as the last part here, I'm going to talk about applying these concepts to analytical measurements. So what most of us do is we try to measure something. And to be able to do that well, we need to establish a few different things. So a typical thing would be to do a titration curve, like as is shown here. So, and this is quite an ideal case where you have from over 2 orders of magnitude, you have a linear correspondence between the theoretical concentration to the measured concentration, and also they lie on the identity line. And then at some point you reach your limit of detection, and below there you can maybe measure something, but it doesn't have really any good correspondence to what actually is in your sample anymore. It's you measuring something, but it's noise, it's contaminants, it's something else. And so to establish these things, so there are a few things that one needs to establish. And this is just a short list that I shown here, and there's actually many more things that people usually, especially if you want to do a clinical test. But in the laboratory, probably these things are enough characters to establish. So the first thing is the accuracy of the measurements and the precision. And this is an important thing to remember. So there's a difference between accuracy and precision. So precision is how close you can reproduce your measurements, while accuracy is how close your measurements is to the real value. Then another thing that's important is robustness. So what happens if the temperature in the room changes while you do your measurement? Or what happens if they're doing construction next door? Like it's happening now, I guess. So that's those are sort of important things to do. The other thing you have to establish is the lower limit of detection. So what is the lowest amount that you can really distinguish from background or negative control? And that's it's still not completely clear how to do that best. There are several ways, but it's still being somewhat debated how to do it. And I'm going to show you one way, actually 2 ways that people do it quite often. Then we have the limit of quantitation. So one thing is to detect, but then you also want to find what's the lowest limit where you can quantify. And then you want to establish over what range your measurement is linear. And why I'm bringing this up here is that for a lot of these things, what we do is we do a few measurements. So we take a sample, we calculate sample statistics like averages, variance, and so on. And that's how we establish how good an analytical measurement is. So the first question is to measure blanks. So what happens? So we want to. We don't add or analyte in. Hopefully we have a system where we don't have any analyte that we measure. So we want to see how much interference there is from other things. So one basic assumption could be that, okay, these measurements are going to be normally distributed. But usually this is a bad assumption. First of all, since we are measuring, we're trying to measure what 0 is, and what, if we have our instrument really calibrated so that our measuring 0 is actually corresponds to the real 0, then we would only see half the distribution. Already there we have a large deviation from a normal distribution. But it's worse than that, because usually the 0 doesn't correspond to the 0 that we measure to a real 0, because it depends on all sorts of things, on amplifiers, so we might actually just so we don't know which of these scenarios we are dealing with. So in this case, trying to use the normal assumption for saying where the blank, what is blank, what is the limit that we should consider nothing, is not good. So here, what we actually, the best way is probably to use, let's say, the 95 percentile of the measurements that we have. So let's say even in this case, if we take the 95 percentile of what we see, or in this case, we will get a reasonably good measure. While if we take the standard deviation and try to use that, we would not. And so that's okay. So I'll come back to that a little bit, how we'll use that. So one other thing that we need to just use, that's often used for analytical measurements, is the coefficient of variation, and that's simply the ratio between the standard deviation and the mean. And this is used often to just characterize how precisely we can measure. So now, if we go back to the lower limit of detection, so there are two different ways that people often do this. One is to say that, okay, we want to have a coefficient of variation that's less than, for example, 20%. It's just an arbitrary number, but that's not, for a lot of applications, that's, it might be 10% in some cases. But anyway, so we say that, okay, we're going to measure the CV and select the lowest concentration where the CV is less than 20%. And this is a practical, quite easy to implement method, but probably not the best. So another method that was proposed in this paper that's cited here is to first you measure the blank, you do many blank measurements, and then you take the 95th percentile of the blank measurements and add a constant times the standard deviation of the lowest concentration that you can measure to get the limit of detection. And that's what's shown here. For example, we have the, for this data, we have the higher line here is the limit of detection, and the lower line is the limit of the blank that we've got from the blank measurements. And so the difference here is the standard deviation. We probably use the few points close to the limit of detection. So that's in both these cases. What we see is that they have rather similar limits of detection in this case. And the points below the limit of detection here are shown in gray, and the other ones in red. And what we can do then is to also fit, so in solid is shown the identity line, so when the theoretical concentration is equal to the measured concentration. And the dotted line is a fit to the data. So in this case, this is very good, looks very good. We get very good linearity over a large range. And then at the limit of detection, we run out of steam. Then another thing that often happens at high concentrations is that our measurement saturates. So we can often see that we get some linearity, but then it plateaus out. And this is quite common. So that's called the upper limit of detection, and this is the lower limit of detection. So then, and between there is when the analytical test is valid. So then if we look at accuracy and precision, so here we see that we have in this measurement quite good accuracy and good precision. So the accuracy would be that the dotted line is almost on top of the solid line, while here we have a systematic shift of our measurements. So that's, but we can then take that into account and maybe compensate for it if we have done these titration curves properly. Okay, so that's the end of this lecture. So then, just to summarize, so we've investigated a few different distributions, a normal distribution, a skew distribution, and one with long tails, and one complex distribution with many peaks. And again, the thing to remember there is that, and that's why we included the complex distribution, is that just because you can calculate the mean and standard deviation, it's not always a good thing to do. For example, for this complex distribution, it's not. So then we talked about mean, median, and quartiles and percentiles that would determine different properties of the distribution. And then also we looked at variance, standard deviation, interquartile range, and how to use these for error bars. And then finally, we looked at a few different ways to display the data and to how to apply these things to analytical measurements. So as I mentioned before, definitely read the Nature Methods statistics blog. They present things in a very clear way, and and they're usually very short and to the point. And then there is this book, Think Stats, that's freely available. That's also presents statistics in a much easier way than usual statistics books do. So next lecture will be given by Stuart Brown on Tuesday, and it's on data types and representations in molecular biology. So then you'll learn a lot about different file formats and databases and how information is stored and transmitted yeah. And if you're interested, so on Saturday, Pam will have a tutorial here in this room, and you're welcome at 3 p.m. Are a lot of people planning to come on Saturday? Or anyone who is planning to come? Okay, good. A few people. That's great. Oh yeah, the other thing I forgot to ask you guys, so who is in their first year? If you can put up your hand. Okay. And second year? And third? And later, 4, 5, 6, 7? Okay, good, thanks. Okay, so yeah, so you have the tutorial on Saturday, and then we'll meet next Tuesday again.